Alright, so today I'm gonna be explaining this important paper with the title Scalable Global Alignment Graph Kernel Using Random Features from Node Embedding to Graph Embeddings. This KDD paper in 2019. Graph kernels are widely used for measuring the similarity between graphs. Many existing graph kernels, which focus on local patterns within graphs rather than their global properties, suffer from significant structure information loss when representing graphs. Some recent global graph kernels, which utilize the alignment of geometric node embeddings of graph, yield state-of-the-art performance. So existing graph kernels just focus on local and ignore the global properties. So we propose a new family of global alignment graph kernels which take into account the global properties of the graph using geometric node embeddings and an associated node transportation based on earth mover's distance. Our graph kernel is obtained by defining distribution over random graphs which can naturally yield random feature approximation. The random feature approximation leads to our graph embedding, which is named as random graph embedding. So random graph embedding is shown to achieve quasi-linear scalability with respect to the number of sides of the graph. So now we assume that a graph G is represented by a bag of vectors. This bag of vectors, we also need to compute weights associated with each node vector. If node V sub I has C sub I outgoing edges, we use this T sub I as a normalized bag of words. And our goal is to measure similarity between a pair of graphs using a proper distance measure. Instead of treating it as an assignment problem solved by maximum weight matching, we cast the task as a well-known transportation problem, which can be addressed by using the earth mover's distance. So one can easily measure the dissimilarity between a pair of graphs through node transportation, which essentially take into account alignment between nodes. A straightforward way that defines a kernel matrix based on earth mover distance that measures the similarity between graphs is like this. You see an illustration on how earth mover distance is used to measure the distance between random graph and raw graph. Each small random graph implicitly partitions the larger raw graph through node alignments in a low-dimensional node embedding space. The core task is to build a positive definite graph kernel that can make full use of both computed geometric node embeddings for graphs and a distance measure considering the alignment of node embedding. So we define the kernel like this. However, fortunately, since we can define our kernel in terms of randomized feature map, it naturally yields the following random approximation that does not require these assumptions. So once you have a data graph, you have n graphs, node embedding, you want to find the feature matrix Z. So this is the compute feature vector using earth mover distance. We generate random graphs and then they calculate the feature matrix. And they use this algorithm for random graph generation. And they did experiments on these data sets, enzyme, mutage, and this is a comparison of classification accuracy. Also, they compared classification accuracy against graph kernel methods.